Hey guys, this is Mr. C. In this video, we're going to talk about discrete linear functions and continuous linear functions. So lesson 4.1 is discrete linear functions, and those are linear functions. That linear means in the shape of a line, the pattern of the graph, and well, that's one way to say it. And discrete just means we're not graphing a line per se, but each of the instances is going to go by, basically in this class, is going to go by ones, little packets or by ones. So for instance, it says lengths of a plumbing pipe are sold in 1-inch increments at a hardware store. A 1-inch pipe costs 60 cents and each additional inch costs 10 cents. And so what we're supposed to do is graph this situation here on this blank graph. So the first thing you want to do is figure out what your independent and dependent variables are. So the independent variable is going to be a length of pipe. And the reason why we'll call that L is because you can't have a cost without a length of pipe. And so cost is going to be the dependent variable. And so we're going to put down here pipe length. And that's going to be in inches. And then on this side, we're going to have cost in dollars. So we'll put cost. Okay. So now let's go ahead, and our graph is blank, so we kind of have to do this ourselves, labeling it. So I'm going to go by ones down here. 1, 2, 3, 4, 5, 7, 8, 9, 10. And we can keep going all the way across here if we want to. I'm going to stop at 10 for now and kind of just see what's going on. And if we go up this axis, we can let our costs here be 10 cents each one of these grid lines. So 10, 20, 30, 40, 50. So this would be 60 cents right here at this one. 10 cents, 20, 30, 40, 50, 60. So 0.60 right there. So here's what it says. A 1-inch pipe costs 60 cents. For a 1-inch pipe, 60 cents. And so we put a dot right there to represent that ordered pair. And it says each additional inch costs 10 cents more. So what's going to happen is 2 inches is going to be 70 cents, 3 inches, 80, 4 inches, 90, and 5 inches is going to be, looks like $1. 60, 70, 80, 90, yeah. So 5-inch, yeah. So now, if you keep going up with this pattern, because it is linear, it's discrete, which means they're only going by so much, then we're going to have this shape of the graph. And we don't connect our dots because our pipe is only sold in 1-inch increments, not half-inch or quarter-inch, but only 1 inch. And so you can only put these ordered pairs on your graph, and that's what makes it discrete. Number 2 says a telephone call costs $2 for the first minute and 50 cents for each additional minute. And so our independent variable is going to be the call length, and that's going to be in minutes. And I'm going to let that be M right there. And that's going to be down here call length. And that's in minutes. And then we're going to have the independent variable. Do this. Independent variable is going to be, or dependent variable, sorry. Dependent variable is cost. And so that's going to be cost in dollars again of the phone call. All right, so now we have to label here. And so what I'm going to do for each grid line down here is I'm going to go by ones again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because these grid lines are so close together, I'm only going to label these for now. And then up here for my cost, if I go by 50 cents each grid line, that would be 50 cents, $1, 50 cents, $2, 3, $4, 5, 6, 7, 8, 9, and finally at the very top, $10. So each one of these grid lines is worth 50 cents. So let's see, a telephone call costs $2 for the first minute. So 1 minute, $2, and we will put that ordered pair on our graph, and 50 cents for each additional minute. So for 2 minutes, it'd go up 50 cents, one grid line. 1, 2, 3 minutes, another 50 cents. And we kind of see that we're using the same pattern we did before to create the rest of our graph here, which if you use different scales for your grid lines, you would get a different looking graph, but it would still be the same situation. And this one, there's your graph for that one. Number 3, it takes 20 minutes to cook a 5-pound turkey and an extra 10 minutes for each additional pound. All right, so we have an independent variable. And this time, normally time is your independent variable, but you can't really have a cooking time without a weight for the turkey. And so the weight of the turkey is going to be the independent variable. So I'm going to put weight down here in pounds. And so I'll use W for that variable. And then on this axis, it's pretty rare, but this time we're going to use time in minutes for the cooking time. Again, like 99% of the time, time is going to be your independent variable, except in this particular one where you can't have a time for cooking without a weight first. All right, so we're going to label these. So we'll go by ones again down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And for our times, we'll go by 5 minutes each time. So it'd go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 55, 70, 80, 85, 90, and 95, 100. All right, so our initial setup, 5-pound turkey is 20 minutes. So 5 pounds, 20 minutes is our first relationship. And it says an extra 10 minutes for each additional pound. So 6 minutes would go all the way up to 30. 7 minutes goes up to 40. 8 minutes goes up to 50. I guess we'll do that one right there. And then we're going to have this pattern for this one. And now we can figure out all the cook times. So 20 minutes to cook a 5-pound turkey, an extra 10 minutes for each additional pound. So it doesn't really say what to do in between, in between the dots. It's just for each additional pound. So there's our setup, our graph for number 3. And number 4 says Burgerland charges $2 for each cheeseburger they sell. And so our independent variable will be cheeseburgers. And let's just go ahead and let that, let's that be, I don't know, C for cheeseburgers. And that's going to go by ones. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right. And now we have the dependent variable, which is going to be money. So that's going to be revenue. And that will be in dollars. Revenue is the amount of money a business takes in from sales. And so we're going to let those go by ones. So 1, 2, 3, 4. 1, 2, 3, 4, $5. Yeah. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. So they get $2 for each cheeseburger. So 1 cheeseburger, $2. 2 cheeseburgers, $4. 3 cheeseburgers, $6. And so we see once we do a few of these dots, we establish a pattern because we know that linear functions always go up or down by the same amount constantly. So there you go. All right, so those are 4 discrete linear functions. And now we're going to talk about continuous linear functions. Continuous linear functions basically are not the opposite of discrete, but you can go between the dots. And a lot of times these will deal with things like time. Time can always be split in half. And so you can always go between two time values. So don't expect most of these to be in time, if not all of them. So the temperature of a cup of water is 50 degrees Fahrenheit, and the temperature of the water decreases 3 degrees every 2 minutes. So we're going to have time down here. That'll be our independent variable in minutes. And then we'll let t be our variable. And we'll go by ones. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And our dependent variable will be temperature. And that's going to be in degrees Fahrenheit. And so that's going to go by, let's see, I think I'm going to go by fives this time. So 5, 10, 15, 20, 30, 40, 50, 60, 70, 80, 90, 100. All right, so this one says the temperature of a cup of water is 50 degrees. So at time 0, it goes up to 50 degrees, and right there. And it's going to decrease 3 degrees every 2 minutes. Now, because I went up by fives each time here, I'm going to have to really be careful about 3 degrees every 2 minutes. So when I drop down 3 degrees, I'm going to have to probably guesstimate where that next dot's going to be. So 3 degrees every 2 minutes. So 2 minutes, it's going to go down to 47, which will probably be right there. 47, 44 for the next one, which will be about right there. 41 for the next one, 6 minutes. 38. 35. That's exactly right there. Let's see, 35, 32, 29, 26, 23, and 20. All right, so when I am graphing these, I'm going to graph the first one and the last one, connect your dots. And I did a pretty decent job of graphing those points. And so there's your continuous linear function is now the graph of a line. Number 2, the temperature at a certain beach was 80 degrees and rose steadily to 90 degrees after 4 hours. So we're going to have time again for our independent variable, and that's going to be in hours this time. T is there, and temperature again in the dependent. And that's going to be in degrees Fahrenheit. All right, so we're going to let the time go up. Let's see, if I skip 4 boxes, 0, 1, 2, 3, 4. So it'll be 1, 2, 3, 4. 1, 2, 3, 4. And 5 all the way over there. And I'm going to let each one of these grid lines for temperature be 5 degrees. So 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. All right, so it says the temperature was 80 degrees. So at the very beginning is 80, is 0, and rose steadily to 90 degrees after 4 hours. So after 4 hours, we're up to 90. So I'm going to go all the way up here. Is that the right one? Yep. And so I'm going to graph those 2 dots. And now I'm going to connect those. And so the thing about these functions are, when you graph your line here, you can interpolate, go in between two data points, or extrapolate, go beyond two data points. And in this case, you could definitely interpolate between these two, but you can't really extrapolate too well because you don't know what happens before the time started or after the 4 hours, because time and temperature are related such that they kind of go up and down like this throughout the course of a day. So, but we can definitely look in between these two dots and figure out what happened in between them. Number 3, after 1 hour of driving at a constant speed, you have traveled 60 miles. After 2 hours, you have traveled 120 miles. So again, we have time down here for our independent variable, and that's going to be in hours. And we'll let that be t. And we're going to have distance for our dependent, and that's going to be in miles. And sometimes I put variables up here, sometimes I don't. I should really get in the habit of doing that. And so the distance we'll call d. And so we're going to make our independent axis here the same as we did up here. We're going to go 0, 1, 2, 3, 4, 1, 2, 3, 4, 2, 1, 2, 3, 4, 3, 1, 2, 3, 4, 4, and then 5 all the way over there. And we're going to go each grid line by 10 miles. So that will go 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. So we have, after 1 hour of driving, you went 60 miles. So 1 comma 60 would be right here. And so 2, 120. Here's 120. And there's 2 right there. So 3 would be 180. 1, 2, 3, 4. Yep. All right, so if we connect our dots here, we should get a straight line. And we do. So if we keep driving at that constant speed, we're definitely able to interpolate and extrapolate on this one. And the last one, number 4. This time we have train speed steadily declines from 100 miles per hour to 70 miles per hour in a 10-minute period of time. So we've got time as our independent again, and that's going to be in minutes. And then we've got speed, velocity, and that's going to be in miles per hour as our dependent variable. And we'll call that actually v. All right, so we're going to go by every 2 grid lines for the time. 1, 2, 3, 4, 6, 7, 8, 9, 10. And we're going to go by every 2 grid lines. It's going to be 10 miles per hour. 10, 20, 30, 50, 60, 70, 80, 90, 100. So it declines from 100 miles per hour at the beginning to 70 in 10 minutes. So after 10 minutes, it's going to go all the way down to 70 right here. And so if it decelerates at a constant rate, we can do a little extrapolation from that. And there is our graph for that continuous linear function. So again, discrete, collections of dots, points, because the things come in, the independent variable comes in little packets, usually ones, but not always. And then for continuous, like time, it's continuous, which means you can cut any interval in the independent variable and you get another member of the interval. Same thing as the domain of these functions are all real numbers whereas the domains of these are usually natural numbers or integers. So remember to like my videos, subscribe to my channel. We'll see you guys later. Bye.